We all rely on these invisible systems every single day, things we just take for granted. Uh, Reliable power, clean water flowing right from the cap. It feels simple, almost magical, doesn't it?
It really does.
But beneath that surface, there's this incredible, often overlooked complexity, and frankly, a ton of hidden costs just lurking in inefficiencies. Today, we're pulling back the curtain on one of those crucial unseen areas, improving reliability and efficiency in pump station control logic. Think of this as your shortcut, really, to understanding a vital piece of our infrastructure. We're drawing key insights, some surprising facts from the latest discussions at WaterJam 2025.
Yeah, it's a hot topic.
We're going to reveal how utilities are making sure that water gets to you not just reliably, but, well, intelligently and sustainably, too.
And our mission for this deep dive is really to unearth the core problems that have quietly plagued these systems for decades. We'll explore the ingenious solutions emerging from advancements in data, AI, and break down the technical concepts that are fundamentally transforming how our pump stations operate. We're going beyond just, keeping things running.
Yeah.
We're looking at how to run them optimally, ensuring long-term health for our infrastructure, and crucially, for our budgets.
Okay, let's dive in then.
Yeah.
If pump stations are essentially the heart of our water and wastewater systems, what's the fundamental problem that's been plaguing these hearts for so long? What are we really trying to solve here?
That's a great question, and it's surprisingly simple at its core. Pumps are often designed for those absolute peak demands, the highest flow rates you could possibly imagine.
Right, the worst case scenario.
Exactly. But here's the reality. Most of the time, they operate at average or even low flows. So this mismatch, it means they're constantly forced to run outside their optimal efficiency range. Imagine driving your car in first gear on the highway. It chews up parts and guzzles gas.
Yeah, terrible.
For a pump, that accelerates wear and tear on critical components like impellers, bearings. The result: expensive, frequent maintenance, and a significantly reduced lifespan for these essential, costly assets.
So it's not just about getting the water from point A to point B, but how it gets there. That detail matters.
Exactly. What's fascinating, and maybe a little concerning, is that current practices, while they definitely ensure reliability, often rely on incredibly conservative hydraulic calculations. They are designed to avoid catastrophic failure, which obviously is paramount for public safety. But this conservatism, while crucial, often inadvertently sacrifices efficiency. It's a trade-off that has real consequences down the line.
And these aren't just theoretical issues, right? I mean, there are tangible challenges that utilities face day to day because of this.
Absolutely. One of the biggest is that exact efficiency versus reliability trade-off you just mentioned. Sometimes running at peak efficiency can conflict with those vital operational safety margins.
Makes sense.
Then there's daily variability. Demand cycles, they rarely match the perfect static design assumptions. This pushes pumps to frequently operate outside their best efficiency point, or BEP, where they perform their best.
Okay, the BEP.
And all of this leads directly to asset degradation. Inefficient operations increase vibration, they raise the risk of cavitation, which we'll definitely talk more about, and ultimately, they lead to the premature failure of parts.
So it's a constant balancing act.
Yeah.
But if these are the challenges, what are the cutting-edge opportunities? What were the experts at WaterJam 2025 really buzzing about to tackle them? This is where it gets really interesting, I imagine.
Indeed. The conversation is really centered around advanced control logic. Utilities are shifting towards using real-time data and even AI, machine learning, to dynamically adjust pump sequences.
Wow.
Imagine the system actually forecasting demand and proactively optimizing pump performance rather than just reacting after the fact.
That's a game changer. So no more static assumptions driving everything.
Precisely. And this leads directly into efficiency modeling. We're moving away from those conservative kind of one-size-fits-all calculations toward adaptive models that intelligently balance efficiency with risk management.
Yeah.
A crucial component of this is condition monitoring. We're talking about deploying various sensors, vibration, temperature, power draw, flow meters.
All sorts of data points.
Exactly. They provide real-time insights, allowing for early detection of inefficiency or potential damage before it becomes a critical, expensive failure.
And what's the bottom line? What's the tangible impact of all this smart technology?
Well, the impact is significant energy savings. Reducing inefficient operation directly lowers power costs, which, for many utilities, is their single largest operations and maintenance expense. It's huge.
I bet.
If we connect this to the bigger picture, the overarching goal is really a fundamental shift. We're moving from those historical conservative calculations toward adaptive, data-driven control systems.
So it's about making our pumps smarter, not just stronger, getting the most out of them for longer, and saving significant money while doing it. That feels like a much more modern approach to infrastructure management.
It absolutely is, and the tangible benefits are clear. Extending asset life by protecting critical components, significantly saving on energy costs, increasing overall system reliability, and, importantly, this also provides leadership with a much stronger case for a clear return on investment, or ROI.
Okay, to really understand how these smart systems achieve those benefits, we probably need to quickly grasp some crucial concepts. First up, I saw this mentioned a lot, the preferred operating region, POR, versus the allowable operating region, AOR. What are these zones and why do they matter so much?
Right, think of it like a pump's personal health zones.
Yeah.
The preferred operating region, POR, is the sweet spot. This is where a pump operates closest to its best efficiency point, that BEP we mentioned. Operating here minimizes vibration, it reduces cavitation risk, which we'll define in a sec, and it lowers mechanical stress. It's a narrower range, representing optimal efficiency and the lowest risk. You could call it the green zone.
The green zone, I like that analogy. So where does the allowable operating region fit in that? Is that like the yellow zone?
Exactly. The allowable operating region, AOR, is a broader range. The pump can still run here without causing unacceptable damage, but efficiency definitely drops and the risk of wear increases. So it's acceptable but not ideal, your yellow zone.
Got it.
The best practice, the goal, is to keep pumps in the POR as much as possible, only allowing temporary operation in the AOR during, say, fluctuating flows or maybe emergencies.
So we really want to keep them in that green zone. But what's the actual danger if we stray too far or too often? What critical concepts are at play here that make staying in the POR so vital?
That's where we get into something called net positive suction head, or NPSH, and a very destructive phenomenon called cavitation.
Okay, NPSH?
NPSH is basically a measure of how much pressure is available at the pump suction compared to the minimum pressure needed to avoid this cavitation problem. There are two parts. NPSH, available, NPSHA, which is the pressure the system provides, and NPSH required, NPSHR, which is what the pump needs, and that comes from the manufacturer.
Right.
The critical part is maintaining a healthy margin, that's simply NPSAOBM minus NPSHR, to ensure reliable operation. You need that buffer.
And what exactly is cavitation? You mentioned it's destructive.
It is incredibly destructive. Cavitation happens when the liquid pressure drops below its vapor pressure inside the pump. This causes tiny vapor bubbles to form in low-pressure areas. Imagine them forming right on the surface of the impeller blades. Then, as the liquid moves to higher pressure zones within the pump, these bubbles collapse, and they collapse violently. This isn't just a gentle pop, it's like micro-explosions happening thousands of times a second. It results in loud noise, intense vibration, pitting and erosion of the impellers, and severe efficiency loss. Long-term, cavitation will quite literally destroy pumps from the inside out.
That sounds nasty. So how does the pump flow rate tie into this NPSH margin and the risk of cavitation actually happening?
Flow rate has a direct impact. At low flow, suction conditions are usually pretty stable, but efficiency is poor, and you can still get recirculation issues causing damage. The NPSH margin might technically be higher, but you're not necessarily safe.
Okay.
Crucially, though, at high flow, when you go beyond the best efficiency point, the NPSHR, what the pump needs, increases sharply because the pump just needs more suction energy to handle that flow. If the NPSH, what the system provides, doesn't rise accordingly, that vital margin shrinks, sometimes drastically.
I agree.
And that leads to a much, much greater risk of cavitation.
Okay, that's a real light bulb moment for me. So staying in that POR green zone isn't just about saving a little bit of energy. It's fundamentally about protecting the pump from being literally eaten away by cavitation.
Yeah.
By keeping that NPSH margin healthy,
Exactly.
it underpins both reliability and efficiency.
Absolutely. So to quickly summarize for you, POR means optimal efficiency and reliability, the green zone. AOR is acceptable but less efficient, higher risks, the yellow zone. Cavitation is that destructive vapor bubble collapse inside the pump, and a healthy NPSH margin is critical. When flow shifts outside the POR, especially too high, that margin often shrinks, making cavitation far more likely.
Okay, that makes perfect sense. So given all this, how do we design these systems from the ground up to avoid those danger zones and hit those sweet spots consistently? The experts highlighted 3 key interconnected steps for reliable pump station design. What's the first pillar?
Right. The first pillar is foundational. Develop an operating envelope. This is literally drawing the safe box of operation for the pump. It defines the minimum and maximum limits for everything: flow, head pressure, NPSH, efficiency, even vibration levels.
Okay.
And within this boundary, you explicitly mark out the preferred operating region, the POR, and the allowable operating region, the AOR.
So it's like mapping it all out. I think I used the analogy before, like your car's speedometer.
Yeah.
The green band for best fuel economy is your POR. Yellow is okay, but not ideal, LOR. And the red zone is damaging and definitely to be avoided.
That's a perfect analogy, exactly. The second step, once you've defined that operating envelope, is evaluate pump selection. You have to match the envelope with the right pump hardware.
Right.
That means choosing the right type: centrifugal, submersible, vertical turbine, whatever fits the application. It means getting the right motor speed and horsepower, and importantly, selecting the right impeller size and trim, because that actually shapes the pump's efficiency curve.
Yeah.
Proper selection ensures the pump actually operates inside its POR under most, if not all, normal flow conditions. Like you said before, you wouldn't buy a race car if your commute is all stop-and-go city traffic.
Right. Pick the right tool for the specific job.
Okay,
so envelope, then pump selection. What's the third pillar?
The third is absolutely critical: prepare functional control. Because even with the perfect pump and a well-defined envelope, it won't matter if the controls run it poorly.
Sure.
This means implementing smart control strategies. Things like well-level controls that decide precisely when to start and stop pumps, maybe constant level controls to keep the downstream system stable, and definitely sophisticated pump sequencing and lag control that intelligently shares the load among multiple pumps, preventing one from getting overworked.
Okay.
And modern controls now often add variable frequency drives, VFDs, or even predictive logic using AI for real-time fine-tuning of pump speed and operation.
So this is kind of like the cruise control in your car analogy again. Intelligently adjusting power input to keep you smooth and efficient, instead of constantly flooring the gas, then slamming the brakes.
Precisely. These three steps, they really work together, not in isolation. First, define those safe boundaries with the operating envelope. Second, choose the right machine with careful pump selection. And third, run it smartly with robust functional controls. Together, they effectively protect against cavitation, extend asset life, and significantly reduce energy costs.
We've talked about functional control, but what's the actual playbook for these smart systems, and maybe what's the brain that executes it all?
Good question. The playbook is what we call the control narrative. This is a crucial written document, really, a specification that explains precisely how a pump station, or really any automated system, is supposed to operate. It details everything: start-stop conditions, maybe based on wet well levels or system pressure, how lead and lag pumps rotate to share the operating hours fairly, what conditions trigger an alarm, and all the critical fail-safes. It's essentially the blueprint before you even start programming the system.
So the narrative is the strategy document. And what's the brain that actually brings that strategy to life in the field?
That would be the PLC, which stands for Programmable Logic Controller. This is the rugged industrial-grade computer, truly the brain, that actually executes the instructions laid out step by step in the control narrative.
Got it.
It's programmed with logic sequences, basically a series of if-then instructions, that mirror exactly what the narrative says should happen. Operators then interact with the PLC, usually through an HMI, a human-machine interface screen, to monitor and sometimes make adjustments to the system.
Okay, so the narrative defines what should happen, and the PLC dictates how it actually happens in the real world second by second. That's a really powerful pairing when you think about it.
It really is. The narrative sets the strategy, lays out the rules, and the PLC is the incredibly reliable industrial-strength quarterback that executes those plays on the field, constantly adapting based on real-time sensor readings and conditions.
Now, once these sophisticated systems are installed and programmed, how do utilities make sure everything is actually running as designed and, importantly, staying efficient over time? It can't be a set it and forget it kind of thing, surely.
Absolutely not. You're right. It requires ongoing validation. This means continuous monitoring. Utilities are constantly reviewing energy use, for example, comparing kilowatt hours used per million gallons pumped against the original design specifications.
Right.
Are we hitting our efficiency targets?
Right.
They're leveraging sensor data review, looking at trends from those vibration, temperature, and flow sensors we talked about to catch inefficiencies or potential problems early. Trending analysis over days and weeks helps spot any drift away from optimal performance.
So looking for patterns.
Exactly. And they're consistently benchmarking performance to ensure pumps are staying within their preferred operating region, that sweet spot, rather than drifting into the less efficient, higher risk AOR.
And is there a critical sort of hands-on test they use out in the field to check this?
Yes, a very important one is the drawdown test. It's a practical, real-world field performance test used to measure actual pump capacity and efficiency under operating conditions.
How does that work?
Well, basically, you start with a known water level in the wet well or maybe a reservoir. You run the pump or pumps, and you measure the time it takes to lower that water level by a specific known volume.
Okay.
From that, you can easily calculate the actual flow rate, which is volume divided by time, and then you compare that measured flow rate to the pump's original performance curve and the design specifications.
And what does that comparison tell them? What's the purpose?
Its main purpose is to confirm that the pumps are actually delivering their expected capacity under real operating conditions. It's often repeated periodically, maybe annually or even more frequently, for critical stations to check for things like wear, potential clogging, or just general reduced efficiency over time.
So what if a pump underperforms on this test?
That's a clear signal. If a pump underperforms on a drawdown test, it's a strong indicator that it might be operating outside its POR. It could be suffering from cavitation damage or experiencing other mechanical issues like impeller wear or bearing problems. This kind of rigorous testing is just crucial. It's the practical, real-world validation that ensures what was designed and programmed is actually delivering the expected efficiency and reliability. It helps catch potential issues before they snowball into critical failures.
Okay, shifting focus a bit from a single pump to the larger system picture. What goes into deciding how many pumps a station actually needs, or, if all the pumps should be the same kind? This feels like a big strategic decision with cost implications.
It absolutely is. For why some stations have 2 versus maybe 4 pumps, it largely comes down to scale and redundancy requirements. Small stations often only need 2 pumps, maybe one size for average flow, and the second identical one for handling peak flows or just serving as a standby if the first one fails.
Yeah, simple redundancy.
Right. Larger stations dealing with much higher flows or wider variations might use configurations like 3 duty pumps plus 1 standby. We call that 3 plus 1. Or sometimes even 2 duty pumps with 2 standbys, 2 plus 2.
And what drives that choice?
The decision factors in the calculated minimum, average, and peak flows the station needs to handle, plus regulatory requirements for what's called firm capacity, meaning the station must still meet certain flow requirements even if its largest pump is out of service.
Oh, okay.
So it's always a balance between the initial capital cost, obviously. Fewer pumps are cheaper up front, and the required level of reliability or risk tolerance. More pumps generally mean more reliability but higher cost.
And what about mixing different types of pumps versus just keeping them all the same? Standardization versus hybridization.
Yeah, that's another key decision. Most utilities strongly prefer standardization, keeping all pumps in a station, and often across their system, the same make and model if possible.
Why that?
It drastically simplifies maintenance, it reduces the inventory of spare parts you need to keep, simplifies the control programming, and makes operator training much easier, so there are lots of operational benefits.
Makes sense.
However, sometimes mixing pump types or hybridization is done. This might happen when a station has to handle vastly different flow conditions very efficiently. For example, you might have one smaller pump optimized specifically for very low overnight flows to save energy, and then larger pumps designed just for handling high peak flows during the day or storm events.
So more complex, but potentially more efficient overall.
Potentially, yes, but it definitely adds complexity to operations, maintenance, and controls. So standardization is usually the preferred route unless there's a very compelling efficiency case for mixing types.
And spares. You mentioned standby pumps, but what about having a complete spare pump unit ready to go? How do utilities budget for something like that, considering they must be pretty expensive pieces of equipment?
They are expensive, yes. Large utilities, especially for their critical stations, often keep at least one complete spare pump unit either on-site or stored in a central regional inventory.
Just in case.
Exactly. While the upfront cost of buying and storing a spare pump can seem significant, the cost of extended downtime, potential environmental issues, and emergency repairs resulting from a catastrophic pump failure is almost always far, far higher.
Right. The cost of not having it.
Precisely. And it's not just the cost of the pump itself. It's crucial to budget for the skilled labor needed, the OT technicians, the electricians, the mechanics for the installation, the control programming, and the wiring during a replacement, which often happens under pressure. Best practice really dictates planning for pump replacements proactively in 5 to 10-year capital budgeting cycles, rather than just reacting to failures when they happen.
That proactive approach seems key.
It is. What's fascinating here is how these strategic decisions really cascade. Each choice, from the number of pumps to the level of standardization and how you budget for spares, reflects a utility's comprehensive approach to balancing long-term performance with operational resilience and overall cost.
Now, what happens when you have multiple pump stations feeding into a single force main? That sounds like it could get complicated, like a traffic jam, but with water pressure. Is that a coordination challenge?
It absolutely can be a major coordination challenge. If 2 or more stations discharge into the same pressurized force main without proper sequencing and control, you run a serious risk of causing hydraulic surges, dangerous pressure spikes, or even backflow from one station into another. Not good.
Yeah, sounds problematic. So what are the solutions?
Well, solutions involve sophisticated coordination, usually through the PLC and the central SCADA system. You program logic to prevent simultaneous pump starts across different stations, for example. Sometimes you install pressure sensors along the force main itself to provide real-time data for adjustments. And in some cases, you might designate one station as the lead station and others as lag stations, where the lag stations only start based on conditions downstream or signals from the lead station. This helps avoid hydraulic conflicts.
And modeling must play a role here.
Oh, absolutely. Crucially, hydraulic modeling is essential during the design phase. The model helps determine the force main's optimal diameter, its length, the elevation profile, all of which dictate how much simultaneous flow the pipe can safely handle without exceeding pressure limits or causing other problems. You have to design the main correctly first.
So it really drives home the point that these pump stations aren't just isolated islands operating on their own. They're part of a complex, interconnected network. It requires really sophisticated coordination and foresight to prevent major issues rippling across the entire system. That's a much bigger, more intricate picture than most people probably imagine when they turn on their tap.
Wow, we've covered a tremendous amount of ground in this deep dive. We went from understanding those hidden inefficiencies and costs in pump stations all the way to the cutting-edge solutions involving advanced control logic, even AI. We explored those critical technical concepts like the preferred and allowable operating regions, POR and AOR, and the really destructive nature of cavitation, plus the importance of NPSH.
Yep, the fundamentals.
We walked through the 3 pillars of reliable design: the envelope, the selection, the control. We understood the playbook role of the control narrative and the brain function of the PLC. And we grasped the ongoing importance of rigorous testing, like that drawdown test, and thinking strategically about system configuration and coordination. And the profound impact of these often unseen advancements, it really can't be overstated. They are fundamentally improving the reliability, the sustainability, and the cost-effectiveness of our essential water and wastewater infrastructure. It ensures that these vital services continue to flow smoothly and efficiently for all of us, day in and day out.
Absolutely. And hopefully gaining this knowledge gives you, our listener, a unique insight into the, frankly, engineering marvels that underpin your daily life, making those simple acts like turning on the tap or flushing the toilet reliably possible.
So maybe a final thought to leave you with. As you go about your day, consider how much more potential for efficiency and reliability might lie hidden in other foundational, sort of unseen systems all around us. Systems just waiting for a similar data-driven deep dive to unlock their full potential.